All right, ladies and gentlemen, welcome to 7.1 Integral as Net Change. So essentially, word problems, or real world, really. And what we're going to be doing is basically using our integrals to help us out. So we're going to first look at this idea called displacement. One you might remember from a while ago. Displacement is basically just the change in position of an object over time. So if you started in the corner of your room or in the center of your room and you walked forward for a little bit of time and then backwards for a little bit of time and then forward and just kept changing your position, the displacement would be how far away from your original point you were. So if we were here, you moved, let's say you moved 5 feet that way, and let's say you moved 8 feet that way, and then you came back and you moved, let's say 6 feet this way. Your total displacement is only the difference between where you started and where you ended. Even though you traveled a total of, 19 feet, you've actually only displaced yourself, If you went 5 feet forward, 8 feet back means you're now 3 feet behind where you started. That means your displacement is only 3 feet, even though the total distance you traveled is 19 feet. All right. Basically, the book describes displacement as the rate of change times time. And what this ends up being is actually, in calculus terms, the integral of the function over the indicated time period. So if you could somehow model this movement in your room as a function, notice that some of it's positive, some of it's negative, some of it's positive, and you recall that our functions, when we found integrals, we were taking the area here as being positive, the area here is being negative, and the area here is being positive, and there was some sort of net change. In this case, it would have been a positive 3 value indicated from 0 to t. So if we took this integral, from 0 to t of my f of x function, whatever this function might have been, we would have said this was equal to 3 because there was a total of 3 left over in the positive direction. Great. Very simple. Nothing outside of what we know how to do already. If you want to find your final position, you just find the sum of the displacement and the initial position. Let's say you were originally, 10 feet from the wall. So your initial position was 10 feet from the wall. Your final position would now be 13 feet from the wall. Let's say that 6 wasn't there. If we went 5 forward, 8 back, your final position would now be just a simple, come on, give me red. This distance here would have been 10 with a -3, which would have been just 7 feet from the wall. So that would be finding your final position. I'm pretty sure most of you guys could figure that out even without me telling you here. All right, total distance traveled, I've kind of hinted at that already, talking about going 5 feet forward, 8 feet back, and 6 feet forward. That's a total of 19 feet. The thing is we didn't count that 8 feet back. So if we went 5 forward, 8 back, and 6 forward again, we didn't count in displacement. We counted this as a -8 because it was directional. However, with total distance traveled, we like to keep everything positive. So if we think about that function we had before, we could say, all right, well, there's a positive version here, a negative version here, and a positive version here. Well, it'd be nice to be able to figure out the whole positive distance traveled. Well, if we were to take this negative bump and move it up here, we could get everything positive. And some of you might realize that this is just the absolute value of f of x. So in red, we have f of x. But in blue, we have the absolute value of f of x, where everything that was below the line, below the x-axis, goes above the x-axis. So that's essentially what we're going to be doing. We're going to be finding the integral, or the area under the curve, of the absolute value of the function. And as I've been saying, this makes it so negative distance is now counted as positive distance, or doesn't have to be distance. I'm just talking about distance here. We can use our calculator to help. We have Math 9, I believe it is, off the top of my head. Yeah, Math 9, the FN int, where we can find the integral of a function, and you actually can plug in absolute value under math as well. You would hit NUM, or go over to the NUM, and would bring up the absolute value button. If we were to do it by hand, what we can do is, I kind of like to do things by hand sometimes. Let's say this was an M, and this is an N, and the total time is T. I could find the integral of f of x from 0 to t dx, but that would find me displacement. But if I wanted to do it by hand, or actually by calculator, I would just type in this, 0 to t of the absolute value of f of x dx. But by hand, I would actually want to do a little bit different. We did this a while ago, talking about total change. And what I would do is I would just break this up into smaller integrals. So this version is positive, so I would find the integral from 0 to m of f of x. And this area here would be negative. So in order to make it positive, I have to subtract the integral of m to n of f of x. Now, you're not going to have to do this a whole lot, but I want to show you kind of how you would do this by hand. And then I would look at this and I go, this is a positive version. I would say, okay, I'm going to add the integral from n to t of f of x dx. Very simple. Obviously, the integral is going to be the same. You would just be evaluating on different intervals. And wherever it was negative, you would want to subtract to make it positive. That's just in case on an AP exam and you need to do it by hand because you're not allowed to calculate in that version, in that piece of the test. And obviously you can use sign charts. Remember sign charts? You would find everywhere where it equals 0 and then just determine, oh, here's positive, here's negative, here's positive. And you don't even have to graph the function, really. You just need to know where it crosses the x-axis. All right, this is just a little reminder for us. If you have forgotten from way back when we first discussed derivatives and stuff like that, this is just a reminder. You have to remember that acceleration is the derivative of velocity, which is the derivative of position. So if I had a s of t function, position, remember we usually use the letter s. Let me write this a little bit better. The velocity is the derivative of the position function. And acceleration would be the second derivative of position. Or if you were only given the velocity function, you would say, okay, that is the derivative. Oops, sorry. Let me get rid of that. If you were given the velocity function, the derivative of velocity is acceleration. Now, I know we're not doing a whole lot of really derivatives here because that's not really the point, but it goes the other direction as well. If you were given an acceleration function, the antiderivative of the acceleration function is velocity. And if you were to take the integral of the velocity function, it's equal to the position function. So if you were given velocity and you wanted to know distance or position, that's what you would be doing. Oops, sorry, let me get rid of, dang it, I keep writing these things wrong. There we go. Okay, the antiderivative of velocity is position. Sorry about this. I hate when it does this. There we go. All right, so these are things that we got to remember here. Anything with change, a rate of change. It could be velocity, it could be anything. When you give it a rate of change and you want to know how much, you would just be finding the antiderivative or the integral of the function. One of the examples in the text talks about potato consumption. You are given a function which is a rate of change. So here's kind of essentially what this problem is working with. It says the rate of potato consumption was this function c of t, which is equal to 2.2 plus 1.1 to the t power. So it's an exponential function. And this is since t is years since 1970. And what they want to know, what was the potato consumption from 1972 to 1973? Or sorry, I read that wrong. It's from the beginning of 1972 to the end of 1973. And that would basically represent the t values from 2 to 4. That's what I misread. Since you're going to the end of 1973, that's basically the beginning of 1974. And since we started at 1970 being 0, this would represent 2 to 4. And it's just essentially the integral from 2 to 4 of my consumption function, of which you can just use your calculator for this particular thing, or you could actually try to do this by hand, integrating this exponential function. It might be a good idea to do every once in a while. All right, so notice it didn't have anything to do with velocity, but it was still a rate of change, and you wanted to know how much. Not how much change, but how much had been used. All right, so it's kind of the same idea here. So there's not much examples because what we're doing today is really just integrating on a closed interval. So integrating from 2 to 4 or thereabouts. All right, so long story short, this is kind of what I'm going to end with here. Essentially what we're doing in this section is using integrals to determine actual real-life problems. The first few examples are just straight math problems. There's no real world thing to them. They're just kind of integrals that we need to calculate. And what I'm trying to get at is this idea. We're not really pointing this out, but you got to remember that Riemann sums, or if I had this, we did this before. You remember LRAM and RRAM and MRAM and all this sort of stuff. Basically taking little rectangles and finding the areas. And that's a Riemann sum, and basically the limit of Riemann sums is our definite integral. All right, I'm going to give you guys this assignment. You guys don't have your assignment sheet yet. I'll give it to you Tuesday, tomorrow. And I think we'll probably make sure we understand this stuff, so it'll take a couple days to complete. We're a little bit ahead of schedule. So we have, I think, 5 sections in this chapter to cover in 3 weeks, I believe. So we'll make sure that we understand this. Yeah, so that's about it for the day. Hope you guys learned a little bit of stuff anyway. At least some of it was a refresher, a reminder. And I will see you guys tomorrow.